Welcome to Understand the Math. In this video, we're going to learn all about transformations of functions, including translation, scaling, and reflections. We'll walk through example problems for each type, and by the end of the video, you'll know how to recognize and graph every transformation step by step. Let's start with vertical and horizontal shifting, also called translations. These move the graph of a function up, down, left, or right without changing its shape. Vertical shifts occur when we add or subtract a constant from the function. Let's start with our graph y is equal to f of x. F of x plus c shifts the graph up by c units. When the graph shifts upward by c, we just add c to f of x. F of x minus c shifts the graph down by c units. When the graph shifts downward, we just subtract c units from f of x. Let's now look at two examples to see how this works. In our first example, we're going to use the graph of f of x is equal to x to graph g of x is equal to x plus 2, and then h of x is equal to x minus 1. Let's begin by graphing f of x is equal to x. F of x is equal to x passes through the origin, so let's put a point here, and then it passes through the point 1, 1. This is then the graph of f of x, and we'll label it f of x is equal to x. To graph g of x, what we're going to do is we're going to shift the graph of f of x upward by 2 units. So each point that we drew for the graph of f of x moves up 2 units for g of x. And this is our graph of g of x. When we graph h of x, we're going to shift the graph of f of x down by 1 unit. H of x is going to pass through this point and then this point. And here's our graph of h of x. Let's now do an algebraic example. Suppose we have a graph of f of x is equal to x squared plus 4, and we want to shift this graph downward by 2 units. What is the equation for this new graph that we're going to call g of x? When we shift f of x downward by 2 units, what we're going to do is we're going to subtract 2 from f of x. Let's go ahead and do that. Our new graph g of x is going to be f of x minus 2. And now let's just plug in what f of x is. That's x squared plus 4 minus 2, which gives g of x is equal to x squared plus 2. And that's our final answer. Let's now talk about horizontal shifts. Horizontal shifts occur when we add or subtract inside the function. Our original function is y is equal to f of x, and looks like this. F of x minus c shifts our graph to the right by c units. When the graph shifts to the right, we just subtract c units from x. I know this seems very counterintuitive. Here's one way to understand this. When x shifts to x plus c, we have to subtract c for the function f of x to stay the same. Let's now look at what happens when we shift a graph to the left. F of x plus c shifts a graph c units to the left. When a graph shifts to the left, we just add c to x. The same reasoning holds as before. If x changes to x minus c, we have to add c for our function value to stay the same. Let's now look at two examples. In our first example, we're going to use the graph of f of x is equal to x That's just like the one we did on the previous page. But now we're going to graph g of x is equal to f of x plus 2, and then we'll graph h of x is equal to f of x minus 3. Let's first graph f of x. It goes through the origin, so we'll put a point here, and then we can graph our function. We'll label this f of x is equal to x. Now let's graph g of x. G of x is going to shift our function 2 units to the left. Remember, when we add 2, we shift 2 units to the left. So let's put our point right here, and then we can graph our function. This is g of x is equal to x plus 2. Now let's graph h of x. We have an x minus 3, which means h of x is going to be shifted to the right by 3 units compared to f of x. So let's take our first point and let's shift it to the right by 3. And then we can go ahead and graph our function. And we'll label this h of x is equal to x minus 3. We're just replacing x with x minus 3. Let's now look at our second example. This example is our algebraic example. It says, suppose the graph of f of x is equal to x squared plus 4 is shifted to the left by 2 units. What is the equation for this new graph, g of x? When f of x is shifted to the left by 2 units, we're going to add 2 to x. This gives g of x is equal to f of now x plus 2. And then in our equation, wherever we see an x, we're going to replace it with x plus 2. So this gives us quantity x plus 2 squared plus 4. And that's g of x. Let's now learn about vertical and horizontal stretching and compression, also called scaling. Vertical scaling occurs when we multiply or divide a function by a constant. Here's our original function, and we're going to begin by stretching it vertically by a factor of c. This is what our function looks like when it becomes stretched vertically, and it's equal to c times f of x. When a graph stretches vertically, we just multiply f of x by c. Let's now look at vertical compression. When we compress a function vertically, it looks like this. Our function is f of x divided by c. When we compress a function vertically, we just divide f of x by c. Let's now look at 2 examples. In our first example, we have a different function than we did in the last 2 examples. We have the function f of x is equal to x squared, and we're going to use this graph to graph g of x is equal to 2 times f of x, and then h of x is equal to f of x divided by 2. Let's begin by graphing f of x is equal to x squared. That function goes through the origin, it passes through the point 1, 1, and then it passes through the point 2, 4. And it looks like this. That's the right side, and now let's graph the left side. I'm going to put a point here just so we know where we're headed. Okay, so we'll label this y is equal to x squared. Now we're going to graph g of x. When we multiply a function by 2, the graph stretches vertically by a factor of 2. Instead of going through the point 1, 1, we're now going to go through the point 1, 2. So let's put these on our graph, and then we can graph g of x. Let's now graph h of x. When we divide a function by 2, it compresses the graph vertically by a factor of 2. So our graph, instead of going through the point 1, 1, is going to go through the point 1, 1/2. So it's going to be a wider graph, and it's going to look like this. We'll label this h of x is equal to f of x divided by 2. And then let's go ahead, and I forgot to label the pink graph. It's g of x is equal to 2 times f of x. And let's just remind ourselves that the x squared is y, or f of x. Multiplying by a constant stretches the graph vertically, and then dividing by a constant compresses the graph vertically. Let's now look at our second example. In this example, it says, suppose the graph of f of x is equal to x squared plus 4 is compressed vertically, let's highlight that, by a factor of 3. What is the equation for the new graph g of x? When we compress f of x vertically by a factor of 3, we have to divide f of x by 3. This gives us g of x is equal to f of x divided by 3, and this is equal to the quantity x squared plus 4 divided by 3. And that's g of x. Let's now talk about horizontal stretching and compressing, or scaling. Horizontal scaling occurs when we multiply or divide x by a constant. When our original function y is equal to f of x is stretched horizontally by a factor of c, we just divide x by c, and we get y is equal to f of x divided by c. This is counterintuitive, just like it was with our horizontal translations. Here's how you can understand this. When we start at x and then go to c times x, and we're stretching the graph horizontally, we have to divide by c in order for our f of x to remain the same value. Let's now look at compressing a graph horizontally. We have y is equal to f of x, and we're going to compress it horizontally by a factor of c. To do this, we are going to have to multiply x by c, and we get y is equal to f of c times x. Again, to make sense of this, we're going to start with x, and we compress horizontally and go to x over c, and when we do this, we have to multiply by c in order for our function value to stay the same. Just to recap, when we stretch a graph horizontally, we're going to divide x by c, and then when we compress a graph horizontally, we're going to multiply x by c. Let's now walk through some examples. In our first example, we're going to use the graph of f of x is equal to x squared. That's just the same one that we looked at on the previous page. And we're going to graph g of x, which is f of 2x, and then h of x, which is f of x divided by 2. Let's start by drawing x squared. I'm going to go ahead and plot some points here just to give us a rough idea of the graph. And we can go ahead and graph it. I'm going to be real careful here. I've never been very artistic, so it's a challenge to make sure it goes through the points. I'm going to go ahead and I am going to highlight this point because we'll need that for graphing g of x and f of x. Let's now graph g of x. G of x is f of 2 times x, which means our graph is going to be compressed horizontally by a factor of 2. So instead of passing through x is equal to 1, it will pass through x is equal to 1/2. That means g of x is going to look like this. So we'll label this g of x, and then I forgot, let's go ahead and let's label this f of x. Now let's graph h of x. H of x is equal to f of x divided by 2, which means we are going to have a horizontal stretching by a factor of 2. So instead of our point being 1, it's going to stretch horizontally by a factor of 2, and it's going to equal 2. So our graph is stretched horizontally and looks like this. And this is h of x. Let's go ahead and also do these algebraically. Our g of x is equal to f of 2x. So wherever we see an x, we're going to replace it with a 2x. So this becomes 2x quantity squared, which gives us 4x squared. Likewise for h of x, wherever we see an x, we're going to replace it with x over 2. So this is x divided by 2 quantity squared, and that gives us x squared divided by 4. Let's now look at our second example. Suppose the graph of f of x is equal to x squared plus 4 is compressed horizontally by a factor of 2. What is the equation for our new graph, g of x? When f of x is compressed horizontally by a factor of 2, we have to multiply x by 2. Remember, compressing horizontally, you multiply. Stretching horizontally, you divide. G of x is then going to be f of 2x. Wherever we see an x, we're now going to replace it with a 2x. So this becomes 2x quantity squared plus 4, which is equal to 4x squared plus 4. And that's g of x. Lastly, let's learn about vertical and horizontal reflecting. I think reflecting is a lot easier to understand than translation or scaling. When we reflect a function vertically, here's our original function. What we're going to do is we are going to reflect it about the x-axis. And we're going to get our new function, y is equal to minus f of x. When we reflect a function about the x-axis, we multiply the function by minus 1 and essentially replace f of x with minus f of x. Now let's look at horizontal reflecting. When we reflect a function horizontally, we're going to reflect it about the y-axis. When we do this, we're going to get the function y is equal to f of minus x. So what we're doing is we're replacing x with minus x. This makes sense because, for example, if we have 2 over here, we're going to have minus 2. So whatever value we have here, we're going to have here. So we just replace x with minus x. Let's now look at our examples. For our first example, we're going to use the graph f of x is equal to x squared, and we're going to graph g of x is minus f of x, and then we'll graph h of x is f of minus x. Let's go ahead and let's first draw our f of x. And we'll label that. Now we'll graph g of x. G of x is minus f of x, so that means we have to reflect f of x across the x-axis. Let's go ahead and let's plug in some points to give us a guide. We're just reflecting it across the x-axis, and then g of x is going to look like this. So this is g of x. Now let's graph h of x. H of x is f of minus x. So x has been replaced by minus x, and that means we're going to reflect the function over the y-axis. I'm going to do some highlighting to show how this works. The right side of f of x is going to flip over the y-axis, and it's going to become this graph. And then the left side of f of x is going to flip over the y-axis, and it's going to become this graph. So it turns out that the graph of f of x and the graph of h of x are exactly the same thing. Let's see why this is algebraically. H of x is f of minus x. So wherever we have an x, we're going to replace it with minus x. So this becomes minus x quantity squared, which is just x squared. So those two functions are the same. g of x is equal to minus f of x. So this is just minus x squared. Let's now look at our last example. Suppose the graph of f of x is equal to x squared plus 4 is reflected horizontally about the y-axis. What is the equation for this new graph g of x? When we reflect f of x horizontally about the y-axis, what we're going to have to do is we're going to replace x with minus x. Let's go ahead and do that. Our g of x is going to be f at minus x. So wherever we see an x, we're going to replace it with minus x. This gives us minus x quantity squared plus 4, which is x squared plus 4. You might notice that this is the same as f of x, just like what happened in example 1. It turns out the reason for this is that f of x is what's called an even function, and when you reflect an even function about the y-axis, you get back the same function. I have a video later in this series that's going to talk all about that. Let's do a quick recap. Translations move a graph, scaling changes the shape of a graph, and then reflections just flip a graph. Be sure to check out my next video where I'll teach you how to graph functions when a lot of these transformations are combined.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.